previous video, we learned how to compare the means of two groups using a t-test. But in public health research, we often need to compare more than two groups. For example, does average BMI differ across age groups? Does blood pressure vary across categories of smoking status? In these situations, we use analysis of variance, or ANOVA. We use ANOVA when our outcome variable is continuous and our predictor variable has three or more groups. For example, comparing BMI across different age groups, blood pressure across regions, or cholesterol levels across BMI categories. ANOVA helps determine whether there are significant differences between these group means. One common mistake is performing multiple t-tests between groups. This increases the probability of false positive results. ANOVA solves this problem by testing all group differences simultaneously, while controlling the overall error rate. In this analysis, we are faced with the task of answering the research question. Does average BMI differ across age groups? We begin by loading our libraries and importing the nChains dataset. Then we create a new variable called age_group. Using mutate and case_when, we categorize participants into four groups: 0 to 17, 18 to 29, 30 to 49, 50 plus. Why do this? Well, in public health research, age is often grouped into meaningful life stages. Risk factors such as BMI frequently vary across the life course. Grouping makes interpretation clearer and allows us to compare population segments more meaningfully than using age as a continuous variable in this context. Next, we create a box plot of BMI across these age groups. This visualization helps us see differences in medians, variation within each age group, and the presence of outliers. Before running statistical tests, we always want to visually inspect the data. Do older adults appear to have higher BMI? Is variability larger in certain age categories? Visualization gives us an intuitive sense of potential differences. Now we run AOV on BMI tilde age underscore group. So what ANOVA actually does is test whether at least one group mean differs from the others. If the ANOVA p-value is significant, it tells us that differences exist, but it does not tell us which specific groups differ. So let's do a little bit of unpacking of results we have here. Our model compared BMI across four age groups. Here's what we found. The F statistic is 1,915 with a p-value of less than 2 times 10 to the negative 16th power. That's written in scientific notation, but what it essentially means is that the p-value is extremely small, far below the conventional 0.05 threshold. In public health research, when the p-value is below 0.05, we consider the result statistically significant. In this case, the p-value is not just significant, it's overwhelmingly significant. So what does that tell us? It means there is very strong evidence that average BMI differs across age groups in this population. Now let's put this into context. The sum of squares for age group is 283,362 compared to 647,898 for the residuals. This tells us that a substantial portion of the variation in BMI is explained by age group differences. In simple terms, BMI is not evenly distributed across age categories. Age appears to be strongly associated with differences in body mass index. From a public health perspective, this is important. It suggests that weight patterns vary meaningfully across the life course. However, ANOVA only tells us that at least two groups differ. It does not tell us which specific age groups are different from each other. To determine that, we would need post hoc tests such as Tukey's HSD. Now we'll run a Tukey post hoc test to determine which specific age groups differ from one another. Remember, ANOVA tells us that at least two groups differ, but Tukey tells us exactly where those differences are. So let's walk through the results step by step. First, we compare children and adolescents ages 0 to 17 to adults. Adults aged 18 to 29 have BMIs that are about 8 units higher than those aged 0 to 17. Adults aged 30 to 49 have BMIs about 10.6 units higher. Adults aged 50 and older have BMIs about 9.9 units higher. All of these differences are statistically significant, with p-values essentially equal to 0. From a public health perspective, this is expected. BMI naturally increases from childhood into adulthood due to growth, body composition changes, and lifestyle factors. Now let's compare adult groups to each other. Adults aged 30 to 49 have BMIs that are about 2.5 units higher than those aged 18 to 29. Adults aged 50 and older have BMIs about 1.85 units higher than those aged 18 to 29. Both of these differences are statistically significant. This suggests that BMI increases from young adulthood into middle age. Finally, we compare adults age 50 and older to those aged 30 to 49. Interestingly, the difference here is about minus 0.7 BMI units, meaning adults 50 and older have slightly lower BMI than those aged 30 to 49. Although this difference is smaller, it is still statistically significant. In public health research, this pattern is common. BMI often increases into middle age and then stabilizes or slightly declines in older adulthood. This may reflect changes in metabolism, muscle mass, survival effects, or health-related weight loss in older age. So, what is the overall story? BMI increases dramatically from childhood to adulthood. Within adulthood, BMI tends to rise into middle age, then slightly decrease after age 50. All pairwise comparisons are statistically significant, meaning these differences are very unlikely to be due to random chance. In the next video, we'll shift from continuous outcomes to categorical data and learn how to test associations using the chi-square test. This method is widely used in epidemiology to study relationships between categorical variables.